Dumbbell Fermions and Spin Models on Honeycomb Lattices.
Okay.
It's by Tom Banks, and it was published, I think it just came out last week, February 13th, 2025, and it dives into some pretty complex physics.
Yeah?
But we're going to break it down for you today.
That's right. We're going to extract the most important nuggets and hopefully make it understandable and engaging, even if you've never seen a honeycomb.
Exactly. Even if the closest you've been to a honeycomb is on your toast. Now, this paper explores a connection between fermions and spins, specifically how they behave when they're arranged on a honeycomb lattice. So maybe let's start with the basics. What exactly are fermions and spins?
So think of fermions as like the building blocks of matter, right?
Okay.
So electrons, those tiny particles that are whizzing around atoms, are a prime example. They're fermions. They make up everything we see and touch.
Okay, got it.
Spins, on the other hand, are a fundamental property of particles. And you can think of them as like tiny internal magnets attached to each fermion. And this influences how they interact with each other.
Okay, so they're like little spinning magnets.
Exactly.
Got it. So all arranging on a honeycomb structure. Why a honeycomb, though? What's so special about that shape?
Well, the honeycomb lattice has some really unique geometric properties that make it very fascinating for physicists.
Okay.
So for one thing, it has this beautiful symmetry and repeating pattern, right?
Okay.
But more importantly, each point on the lattice has exactly 3 nearest neighbors.
Okay.
And that turns out to be really crucial for the theoretical model in this paper.
I'm starting to see the appeal. But now we have to introduce the stars of the show.
Mm-hmm.
Dumbbell fermions.
Uh-huh.
The name makes me think of, like, tiny weightlifters.
Right.
Seems a bit out there.
It's a quirky name, I'll give you that. But it actually makes sense when you visualize it. So imagine each fermion is a dumbbell, not lifting weights, but connecting 2 points.
Okay.
One on the honeycomb lattice and another on what we call the dual lattice.
Dual lattice. Okay, now I'm really lost.
So think of it like this, right? You overlay another honeycomb on top of the original one, but shifted so that each new point sits in the center of an original hexagon.
Uh-huh.
That's the dual lattice, kind of like a hidden pattern within the honeycomb structure.
Okay.
And these dumbbell fermions act as bridges between these 2 lattices.
I'm trying to picture it in my mind. It's like looking at a honeycomb through a special lens that reveals a secret layer underneath.
Exactly, exactly. And this idea of connecting 2 seemingly different lattices through these dumbbell fermions is at the heart of this paper's most fascinating discovery, a concept called duality.
Duality? That sounds pretty profound. What does that mean in this context?
So in physics, duality means that 2 seemingly different things are actually mathematically equivalent.
Okay.
It's like discovering that 2 completely different recipes lead to the same delicious cake.
So 2 different ways of describing a same reality.
Precisely. And what's remarkable here is that this paper reveals a duality between models of these dumbbell fermions, which have a specific kind of symmetry, and models of spins on a honeycomb lattice, the kind that was studied extensively by Alexei Kitaev,
Okay.
a leading physicist in the field of quantum computing.
Wait, so this paper connects these theoretical dumbbells to the work of a top physicist exploring quantum computing?
Yeah.
That's a pretty big deal.
Yeah.
But how do they actually show this duality? It sounds like some pretty intense math.
You're absolutely right. The math gets pretty complex. But the core idea is surprisingly elegant. They found a way to rewrite mathematically the interactions between spins on the honeycomb lattice as interactions between these dumbbell fermions.
So it's like they've created a Rosetta Stone,
Yeah.
translating between the language of spins and the language of fermions.
That's a fantastic analogy. And what's brilliant about this translation is it allows physicists to approach problems from a completely new angle. Imagine trying to solve a puzzle with the wrong pieces. It's nearly impossible. This duality gives them the right pieces to understand the behavior of these systems in a much deeper way.
Okay, now I'm really intrigued. What are some of the insights this duality reveals? Like, what can we learn about these systems by looking at them through this new lens?
Well, one of the key things that it allows us to do is to study how different patterns of what we call flux on the honeycomb lattice affect the behavior of the fermions.
Hold on, rewind a bit. What do you mean by flux in this context?
So imagine a magnetic field, right, passing through the honeycomb lattice.
Okay.
This creates a pattern of flux. And different patterns can lead to completely different behaviors in the fermion model. It's like changing the terrain on which these dumbbell fermions are moving.
So by adjusting this magnetic field, we can essentially create different landscapes for these fermions to explore, which in turn affects their behavior.
Exactly. And this leads to an incredible diversity of possibilities. What's fascinating is that a single spin model, like the ones Kitaev studied, can actually give rise to an infinite number of different fermion models.
Wow, infinite possibilities from a single model.
Yeah.
That's mind-boggling. What are some examples of these different fermion models that emerge?
Well, the paper provides some really interesting examples. One is what happens when there's no flux at all. It's kind of like a flat, featureless landscape for the fermions, right?
Okay.
In this scenario, the model behaves very similar to the electrons in graphene.
Graphene, the wonder material that's supposed to revolutionize everything from electronics to building materials.
That's the one. So understanding this simple, fluxless model could give us insights into the behavior of real-world materials like graphene, and potentially help us design even more exotic materials with unique properties.
That's incredible. So just by tweaking the flux, we could potentially unlock a whole new world of materials with amazing properties. What other examples did they explore in the paper?
Well, they also look at what happens when you have a constant magnetic field,
Okay.
which creates a very specific kind of flux pattern. And in this case, the fermion model behaves completely differently, with a distinct, what we call dispersion relation.
Dispersion relation, that sounds a bit technical. Can you break that down for us?
Of course. So imagine you throw a ball, right? How fast it goes and where it lands depends on how you threw it.
Right.
The dispersion relation is kind of like that, but for these tiny particles, it describes how their energy relates to their momentum, essentially, how they move and behave.
Okay, that makes sense. So different flux patterns lead to different dispersion relations, which means that the fermions behave differently in each scenario. It's like each landscape dictates its own set of rules for how the fermions can move and interact.
Exactly. And what's even more exciting is that the paper hints at the possibility of extending these ideas beyond the flat 2D honeycomb lattice into higher dimensions.
Whoa, going 3D. That sounds like a whole new level of complexity, but can you even apply this dumbbell model in higher dimensions?
That's the challenge. To make this work in higher dimensions, you need to find lattices where each point still has exactly 3 nearest neighbors on the dual lattice. It's a very specific geometric requirement.
So it's like finding a 3D version of the honeycomb puzzle, making sure each piece fits perfectly with its neighbors. That sounds pretty tricky.
It is, but the paper mentions that there are already some examples of 3-dimensional lattices that might fit the bill, like certain types of Kitaev models.
So physicists are already on the hunt for the right 3D lattice that could unlock this whole new level of understanding.
Exactly.
So before we were talking about how changing the flux patterns, like the landscape these particles are moving on, can lead to completely different fermion behavior, even create a model that mimics graphene.
Yeah, that's just one of the amazing things this duality reveals. By rewriting the problem in terms of these dumbbell fermions, we gain a whole new set of tools to manipulate and control these systems.
Now that's what I call putting theory into action. So how does this actually translate into actual control?
Well, we've spent decades studying fermions, especially in the context of electronics and material science.
Right.
We've learned to manipulate electric and magnetic fields to control the flow of electrons. That's the basis for things like computer chips and transistors.
So you're saying we might be able to apply similar techniques, the same know-how, to these dumbbell fermions, even though they're theoretical constructs.
Precisely. And because of this duality, by controlling the fermions, we indirectly control the spins as well. It's like having a set of puppet strings. Adjusting one affects the other in a very predictable way.
So by tweaking the flux patterns, these magnetic fields, we could orchestrate a whole dance of these fermions and spins on the honeycomb lattice.
That's the idea. This opens up incredible possibilities for designing new materials with tailored properties.
Okay.
Imagine creating materials that are superconductors at room temperature, or they can change their properties on demand based on the applied magnetic field.
Okay, now you're talking about things that sound straight out of science fiction.
Right.
But wouldn't there be massive hurdles to overcome before we can actually engineer materials at this level of precision?
Of course, we're still in the early stages of exploring these concepts.
Yeah.
But that's the beauty of theoretical physics. It allows us to dream big and envision possibilities that might seem outlandish today, but could become reality tomorrow.
It's like we're planting seeds of ideas that might take years, even decades, to fully blossom. Speaking of expanding our horizons, the paper also touches upon the idea of taking this model into higher dimensions. Where does that lead us?
Yes, the quest for higher dimensions. It's a challenge, as we mentioned before, because you need to find lattices that fulfill specific geometric requirements for this duality to work. Not every lattice is compatible with these dumbbell fermions.
So it's like finding the right 3D puzzle pieces that fit together perfectly, extending this intricate honeycomb pattern into something even more complex. Why is this geometric compatibility so crucial?
Remember, each dumbbell connects a point on the lattice to a point on the dual lattice.
Right.
The specific way they interact, based on the lattice structure, is what makes this whole duality work. If the geometry isn't right, the mapping between spins and fermions just breaks down.
It's like a delicate dance. The steps have to be perfectly synchronized for the performance to work. So what are some potential candidates for these higher dimensional lattices?
The paper mentions three-dimensional Kitaev models as potential candidates. These models have shown some promise in other areas of physics, and they possess this necessary three nearest neighbor connectivity that might be compatible with this dumbbell fermion framework.
So physicists are already on the hunt for the right 3D lattice that could unlock this whole new level of understanding. But before we get lost in higher dimensions, I have a question that's been bugging me. We keep talking about the honeycomb lattice and its dual lattice as if they're separate entities. But aren't they both just part of the same space?
That's a very astute observation. You're absolutely right. They do exist in the same space. But visualizing them separately helps us grasp the concepts more easily. Think of it like looking at a city map.
Okay.
You might have one layer showing streets and buildings, another showing subway lines, and yet another showing elevation contours. They all represent the same city, but highlight different aspects.
Ah, that's a great analogy. So the lattice and its dual are like different layers of the same map, each revealing a different perspective on the same underlying reality.
Exactly. And the dumbbell fermions are like little shuttles traveling between these layers, carrying information and highlighting those hidden connections.
I love that visual. But if they're just different perspectives, why do we even need to talk about a dual lattice? Why not just stick with the original honeycomb?
That's where the magic of duality comes in. By introducing the dual lattice and these dumbbell fermions, we gain a whole new language to describe the system. This new perspective might seem more abstract, but it reveals hidden patterns and connections that were invisible before.
It's like putting on a special pair of glasses that allows us to see things in a completely new light, things that were always there, but hidden from our ordinary view. So it's not just about the physical structure of the lattice, it's about the way we choose to see it, the language we use to describe it.
That's a profound insight. Theoretical physics is often about finding the right language, the right framework to unlock the secrets of the universe. And this paper, with its concept of duality, has given us a powerful new tool to do just that.
Well, I'm definitely feeling a sense of awe and wonder at the intricacies of these theoretical models and the potential they hold. But let's not get ahead of ourselves. We've been discussing this paper at length, but what are the key takeaways for our listeners? What should they remember about this research?
First and foremost, this paper highlights the incredible connection between spins and fermions on a honeycomb lattice. It's a relationship so deep that they can be described as two sides of the same coin, two expressions of the same underlying physics, thanks to this idea of duality.
Right. It's like they're dancing partners, forever intertwined in this complex and beautiful choreography.
Exactly. And this connection is not just some mathematical curiosity. It has potentially profound implications for understanding materials, developing new technologies, and even exploring the frontiers of quantum computing.
It's like opening a door to a whole new world of possibilities, a world where we can manipulate and control matter at the most fundamental level.
The second key takeaway is that the paper provides us with a powerful new framework, this dumbbell fermion model, for understanding and manipulating these systems. By switching to this new perspective, we gain access to a whole new set of tools and insights.
It's like being given a new language,
Yeah.
a new way of thinking about the universe.
Precisely. And finally, the paper opens up some exciting new avenues for future research, particularly in the realm of higher dimensional systems. While there are challenges to overcome, the potential rewards are immense.
It's a call to action for the next generation of physicists to take these ideas and run with them, to explore uncharted territory and unlock even deeper mysteries.
Absolutely. This paper is just a starting point, a glimpse into a vast and intricate universe of possibilities. It's an invitation to push the boundaries of our understanding and to embrace the unknown with curiosity and wonder.
It's really amazing how these seemingly abstract concepts can open up like entirely new ways of thinking about the universe.
You know what I think is really fascinating is how this research might be hinting at something even deeper.
Okay.
Something beyond our current understanding of the building blocks of matter.
Okay, you've definitely piqued my curiosity. What do you mean by deeper? We've been talking about fermions and spins.
Right.
These tiny particles that make up everything around us. What would be more fundamental than that?
Well, what if the universe at its most fundamental level isn't built on particles at all?
Okay.
What if these models with their honeycombs and dumbbells and dualities are pointing us towards a completely different picture of reality.
Whoa, now that's a mind-blowing thought. Are you suggesting that our current understanding of particle physics is somehow incomplete? That there's a whole other level of reality we're not yet grasping?
It's certainly a possibility worth considering. Perhaps the universe at its core operates on principles that are so foreign to our everyday experience that we struggle to even conceptualize them. Maybe these mathematical models, these intricate relationships between spins and fermions, are our first glimpses into this hidden realm.
So it's like we're using these theoretical tools to kind of explore the edges of a vast uncharted territory,
Yeah,
a territory where our familiar notions of particles and space-time might just break down completely. It's both exhilarating and a little bit terrifying to think about.
exactly. And that's what makes scientific exploration so captivating, right? It's about venturing into the unknown, challenging our assumptions, and being open to the possibility that the universe is far stranger and more wondrous than we can imagine. This paper, with its exploration of duality and its hints at higher dimensions, is a perfect example of that spirit of discovery.
It's a reminder that we're constantly pushing the boundaries of knowledge, refining our understanding of the universe with each new, insight, each new discovery, and who knows what incredible revelations await us on this journey of exploration.
It's a journey that never truly ends. Each answer leads to new questions. Each discovery opens up new avenues of exploration. And that's what makes science such a thrilling and endlessly fascinating pursuit.
Well said. And on that note of cosmic wonder and endless curiosity, we come to the end of our deep dive into the world of dumbbell fermions and spin models on honeycomb lattices.
It's been a true pleasure sharing this intellectual adventure with you.
And to our listeners, thank you for joining us on this deep dive. We hope you've come away with a newfound appreciation for the power of theoretical physics to illuminate the hidden connections that govern our universe. And perhaps even a sense of inspiration to explore these ideas further. Remember, curiosity is the key that unlocks the doors to knowledge, and the universe is full of mysteries waiting to be unraveled.
Keep questioning, keep exploring, and never stop diving deep.
Until next time, happy diving!